All right, let's get right into it. There's this new theoretical physics paper out there that's been stirring things up, suggesting something pretty huge about the future of particle physics. So we're going to break down what it actually says.
I mean, it's a massive question, right? For decades, the name of the game has been building bigger and bigger colliders to smash particles at higher energies, all in the hopes of finding new, heavier ones. It's exactly how we found the Higgs boson. But what if? What if there's an end to that road?
You've probably seen the headlines flying around, maybe suggesting that this study proves we've hit a wall, that building a successor to the Large Hadron Collider would just be a total waste of money. Now, that is a very bold claim. And yeah, it's causing quite a stir. And that brings us to the real question we're here to answer. We're going to cut through all the noise and go straight to the source. We'll dig into the paper itself to understand the model, the predictions, and, this is crucial, the limitations.
Okay, so first things first, let's set the scene here. What's the fundamental problem this paper is even trying to tackle in the first place?
You know, this standard model of particle physics is, well, it's unbelievably successful. But it has this one really nagging gap. It can't predict the masses of particles like electrons or quarks. It's like having a brilliant recipe that tells you exactly how to combine ingredients, but it doesn't tell you how much of each ingredient to use. Physicists have to measure those values and just plug them in by hand. And that's where this new paper comes in. It's an attempt to finally explain where those numbers come from. So to do this, the author, H.D. Herrmann, put some pretty new and I should stress very theoretical ideas on the table. Let's walk through the core concepts. And the central idea is, well, it's pretty wild. The model basically says that particles live a double life. They exist in our normal spacetime, sure, but their properties, like mass and spin, are actually generated in a separate, hidden circular space that's unique to each particle. It's kind of like a watch, right? You see the hands moving on the face, that's our spacetime, but the real work, the gears turning and making it all happen, is happening in a hidden space behind the scenes. And the fundamental gear in that hidden mechanism? It's called a biraton. You can see it here. It's the structure with two parts spinning in opposite directions. And get this, in this model, every fundamental particle we know, an electron, a quark, you name it, is actually just one of these biratons, doing its thing in its own little private space. Now, this leads to an absolutely crucial assumption in the model. It says that mass isn't a smooth, continuous thing that can have any value. Instead, it's quantized. It comes in these tiny, fundamental, indivisible packets. It's just like money. You can have a penny or 2 pennies, but you can't have half a penny. Mass, in this model, has a smallest possible unit. So, how big is this packet of mass? Well, to figure that out, the author does something pretty clever. He takes the particle we know really, really well, the muon, and kind of reverse engineers it to find the size of that fundamental building block. The value he lands on is about 3.3 mega-electron volts, and the idea is that every other particle's mass is just built up from multiples of this one basic number. All right, quick recap. We've got our hidden space, we've got our spinning biraton, and we've got our tiny packets of mass. So, how do we get from that to the actual particles we see in experiments? So, the model describes a particle as having two main components, which it calls the skeleton and the dress. The skeleton is pretty much what it sounds like. It's the core structure, the bulk of the mass, built by combining a certain number of those mass quanta. And then there's the dress. This is what's on the outside. It's made of circulating charges, and it's what determines how the particle behaves and interacts with everything else. Let's make this real with that same example from the paper, the muon. Now, I know this table looks like a lot, but don't worry about all the details. Just focus on that skell column for skeleton. See how it's built from rings of MQ? That's our mass quantum. And if you add it all up, the model says the muon skeleton is made of exactly 32 of these mass packets. The rest of the table is just describing its dress. Okay, so that works for a pretty light particle, like the muon. But what about the really heavy hitters, like the top quark? It's way, way heavier. How does the model explain that huge jump? Well, it introduces a new trick, something called charge clusters. Think of these as little turbochargers. They're neutral groups of charges that circulate with the mass quanta and, poof, they make each quantum massively heavier. And this is where it all clicks together and becomes really compelling. Take a look at this chart. On the bottom, you have different generations of particles. Going up, you have their mass. And notice, that's a logarithmic scale, so each step up is a huge jump.
The model combines two things: the number of mass packets, which goes up nice and steady, and this enhancement factor from the charge clusters, which just explodes upwards. The result? That solid red line. And look how closely it matches the actual measured masses of the particles. Those are the little circles. It's one single function that seems to describe them all.
Okay, so this brings us to the headline-grabbing claim, the whole reason we're talking about this. How on earth does this model predict a hard stop, an upper limit to how heavy a particle can be? Well, if you just take that red line from the last chart and just keep it going upwards, the formula predicts there should be another super heavy particle component sitting way up at the top. The author calls it a big parton, and the model predicts its mass should be right around 1.5 tera-electron volts, or TeV. Now, to give you some context, 1.5 TeV is smack in the middle of the energy range the LHC has been exploring for years. And there's the rub. If the model's right, we probably should have seen this thing by now. But we haven't. It's not there. So what gives? This is where the paper makes its most important leap, its central hypothesis.
The author's proposed answer is pretty elegant, actually. He says the big parton is fundamentally unstable. It can't ever actually form. The idea is that once it gets to that specific size, its internal structure just breaks apart. As you can see here, instead of one giant 1.5 TeV particle, it immediately splits into smaller, more stable components that look a lot like things we have seen. And this is really the punchline of the whole paper. This table shows what those split pieces become. Look at the middle column. When the big parton splits into two fractions, the model predicts you get the Z boson and a component of the Higgs boson. When it splits into three fractions, you get another Higgs component. This is the key. The model isn't just saying there's a limit. It's using that proposed limit to explain the masses of particles we've already discovered.
Okay, that is a really neat self-contained story, right? It all fits together beautifully, within the model's own logic. But now we have to take a big step back and talk about what this paper is, and maybe more importantly, what it is not. And honestly, this is the most important part of this entire explainer. I want to be crystal clear here. This is a theoretical model. Full stop. It does not prove an upper mass limit exists. It proposes a conjecture. The entire idea of this limit comes from the internal logic of this one specific, unproven model. There is no new experimental data here. This paper doesn't invalidate the standard model. It just offers an alternative way to think about where particle masses come from. So you might be thinking, okay, if it's just one unproven idea, why is it getting so much attention? Why are we even talking about it? And the reason physicists find this work so intriguing is because of its ambition. It tries to explain the entire spectrum of hadron masses, a huge range of energies from the pion all the way to the top quark, with a single, elegant mathematical function. Whether the model turns out to be right or wrong, that attempt itself is a powerful and very appealing idea. And this quote from the author himself really frames the biggest implication. If his conjecture is right, it suggests that the energy region above a certain point is empty of particles, an absolute desert. A particle desert. That's a powerful image. And the practical consequence of that, if it were true, would be profound for the future of physics. It might mean that building vastly more powerful and expensive colliders to search for new particles is the wrong strategy. Maybe the future is instead about building machines to study the particles we already have with much higher precision. But let's end where the author ends, with scientific caution. He explicitly states right there in the paper that his prediction of a desert could be proved wrong, and then the main point of this article would become obsolete. You have to respect that honesty. So, what can we responsibly say? We can say that this paper presents a novel, internally consistent model with a testable, provocative prediction. It's an idea, a very interesting idea, but for now, it is not yet a fact.